Have you ever stopped to wonder where gold actually came from? Not who mined it, not which country owns the most of it, but where it truly originated. Because here's the strange part. Earth never had the power to create gold in the first place. The temperatures inside our planet aren't high enough. Even the sun, a massive nuclear furnace burning at millions of degrees, cannot produce it. And yet, gold exists here, buried in rock, shaped into jewelry, sitting inside the device you're holding right now. So how did something our planet cannot manufacture end up scattered across its surface? The answer is not geological, it's not chemical, it's cosmic. To understand why this works the way it does, we have to start at the beginning. In the earliest moments of the universe, there was almost nothing complicated. After the Big Bang, the cosmos was a hot, expanding sea of simple particles. As it cooled, the first atoms formed. But they were basic, mostly hydrogen, which has one proton, some helium, which has two, a trace of lithium. That was it. No gold, no iron, no oxygen, just simplicity. Every element is defined by the number of protons in its nucleus. Gold's atomic number is 79. That means every atom of gold contains 79 protons bound tightly together at its core. To build gold, nature had to assemble 79 positively charged particles into one stable structure. That is not easy. Protons repel each other. Forcing them together requires extreme pressure and temperature. Stars are the universe's first attempt at solving that problem. Inside stars, nuclear fusion pushes protons together under crushing gravity. Our Sun fuses hydrogen into helium. Larger stars go further. As they age, they begin to fuse helium into carbon, carbon into oxygen, and oxygen into silicon. The ladder continues upward. With each step, the star needs higher temperatures and greater pressure to keep the reactions going. Eventually, in the most massive stars, fusion reaches iron. Iron is the turning point. Fusing elements lighter than iron releases energy, which keeps the star stable. Fusing elements heavier than iron requires energy instead of producing it. Once a star's core fills with iron, it can no longer generate the outward pressure needed to resist gravity. The core collapses. The star dies. So here's the problem. Even the largest stars in the universe cannot produce gold through normal fusion. They do not have the energy budget to keep building heavier and heavier nuclei past iron in any significant amount. For years, scientists suspected that supernova explosions, the violent deaths of massive stars, might create gold. When a star collapses and explodes, temperatures spike, and particles scatter in all directions. Supernova do produce many heavy elements, but observations suggested they might not account for all the gold we see. The real answer turned out to be even more extreme. When certain massive stars collapse, their cores compress into neutron stars. These objects are difficult to imagine. A neutron star packs more mass than our Sun into a sphere only about 20 kilometers wide. Its gravity is immense. Its matter is so dense that atoms themselves are crushed, leaving a sea of neutrons pressed tightly together. Now, picture two neutron stars orbiting each other in deep space. Over millions of years, they spiral inward, losing energy through gravitational waves. Their orbit tightens, their speed increases, and finally, they collide. This collision is called a kilonova. For a brief moment, conditions become almost incomprehensible. Temperatures soar into the billions of degrees. Matter is thrown outward at a significant fraction of the speed of light. But the crucial ingredient is not just heat. It is neutrons. In this violent merger, atomic nuclei are bombarded by vast numbers of free neutrons in a process called rapid neutron capture, or the R process. Instead of slowly adding protons through fusion, existing nuclei are flooded with neutrons so quickly that they become unstable. These neutron-heavy nuclei then undergo radioactive decay, transforming neutrons into protons. Step by step, they climb the periodic table. Some of those transformed nuclei settle into stable forms, including gold. In a single neutron-star collision, an astonishing amount of heavy elements can be created. Observations of kilonova events suggest that they can produce more gold than the total mass of several Earths. That gold, along with platinum and other rare elements, is blasted into space as debris. Over time, that debris mixes with gas clouds drifting through galaxies. Eventually, those enriched clouds collapse under gravity and form new stars and planetary systems. Our solar system was born from one of those recycled clouds about 4.6 billion years ago, which means the gold on Earth predates the planet itself. But there is another twist in the story. When Earth first formed, it was not the calm, solid world we know today. It was molten, a sphere of magma and violent impacts. As it cooled and differentiated, heavy elements began to sink. Gold is extremely dense and chemically attracted to iron. As Earth's iron core formed, most of the gold present at that time followed it downward. Today, deep in Earth's core, there is likely an enormous amount of gold locked away, permanently inaccessible. Some estimates suggest there is enough to coat the planet's surface in a thick layer, but it might as well be on another world. So why do we find gold in the crust at all? The answer lies in a chaotic period known as the Late Heavy Bombardment. Roughly 4 billion years ago, the inner solar system experienced a surge of asteroid impacts. These objects, remnants from planetary formation, were rich in heavy elements forged in ancient stellar collisions. When these gold-bearing asteroids struck Earth, they delivered fresh material to the surface. Unlike the gold that had already sunk to the core, this incoming gold remained in the crust and upper mantle. Over hundreds of millions of years, geological processes concentrated it. Hot fluids moved through cracks in rock, depositing gold in veins. Tectonic activity shifted and exposed deposits. Rivers eroded rock and carried flakes downstream. Every gold nugget ever discovered is part of that long chain of events. From a neutron-star collision to an interstellar cloud, from solar system formation to asteroid impact, from molten Earth to tectonic uplift. Gold is not just rare because of supply and demand. It is rare because its creation requires an event that may happen only occasionally in a galaxy. It demands the collapse of stars, the formation of neutron stars, and a perfectly timed collision. And yet, here it is. We melt it into rings. We store it in vaults. We embed it in electronics because it resists corrosion and conducts electricity reliably. It becomes a symbol of wealth, stability, and permanence. But its true story is anything but calm. Every atom of gold in your jewelry survived forces so intense they reshaped atomic nuclei. It endured a journey across interstellar space, lasting millions or even billions of years. It became part of a planet that nearly lost it to its core. It was delivered again by asteroids. It waited underground until humans learned to dig. When you hold gold, you are holding the aftermath of a stellar catastrophe. It is one of the few materials on Earth that carries a direct fingerprint of an event beyond our solar system. Not metaphorically, physically. The atoms themselves were forged in a collision between the collapsed remnants of dead stars. We often call gold precious because it is scarce and beautiful, but perhaps it is precious for a deeper reason. It is a reminder that the universe is not static. It is dynamic, violent, and creative. The same processes that destroy stars also build the ingredients of worlds. The next time you see gold glint in the light, consider its journey. It did not begin in a mine. It did not begin in a volcano. It began in darkness, under pressures and temperatures that push matter to its limits. Gold exists because the universe is capable of extraordinary events. And somehow, the debris from those events became part of our everyday lives. That may be the most remarkable part of the story. So the next time you see gold, remember this. It wasn't born on Earth. It was forged in a collision between dead stars, scattered across space, delivered by asteroids, and buried for billions of years before we ever found it. Gold is rare not just because it's hard to mine. It's rare because the universe rarely makes it. Thank you for watching. If there's another everyday object you'd like to trace back to its true origin, let me know. And if you enjoy explanations like this, consider subscribing.